So our second presentation is by Dr. Aaron Gallant. The title will be or is Accelerated Carbonation for Soil Stabilization. Aaron earned his BS in Civil Engineering from Tufts University and went on to pursue his master's and doctorate in Civil Engineering from Northwestern University, specializing in geotechnical engineering. His research interests lay in combining theory and practice to reconcile observed performance and behavior of natural landforms, geomaterials, and subsurface infrastructure with emerging interest on ground improvement stabilization, behavior of gassy, unsaturated sediments, and resiliency to instabilities during extreme events and dynamic loading and soil structure interaction. Got pretty much everything there. He previously worked as a geotechnical engineer at CH2M Hill in Virginia before coming to teach in the Civil and Environmental Engineering Department at the University of Maine in 2016. He is a member of the American Society of Civil Engineers, the Deep Foundations Institute, and the U.S. Universities Council on Geotechnical Engineering Research. Aaron, floors are yours.
It's always fun to have Aaron introduce Aaron. So, thank you all. Today I'm going to be talking about accelerated carbonation here to stabilize subgrade materials. I've worked on this with my colleague Warda Ashraf, and I forgot to put his name up here, but also Luis Zambrano, who's in the Civil and Environmental Engineering Department at University of Maine as well. We've had several students working on this project as well. You see them listed here. And then we got some fun photos below. So today what I'd like to do is kind of talk about this sustainability topic from a materials perspective. I'm not going to get into the ton of weeds on necessarily the work or technical work that we've done here today, but kind of think about what it's going to take to push these materials forward. What are we going to do to start getting departments of transportation, municipalities, public agencies, contractors using these? And I'll talk about some of the challenges kind of at the end here that I see moving forward. One of the topics that you've probably heard about is that cement, all right, basically emits a lot of CO2. All right, it accounts for 8-9% of global emissions worldwide. So this is something that the materials industry, civil engineering industry is certainly trying to combat. And we think about climate goals, particularly the Paris Accord. When we're starting up here at 2.7 gigatons annually, and we want to get down to 0.7 by 2050, that's quite a decrease. All right, that's a substantial decrease. And folks are talking about different ways, increasing energy efficiency with the kilns, alternative fuels, clinker substitutes, and others. But really the big one here that you see, 2/3, we're relying on new technologies. All right, basically 2/3 of what that reduction will be is relying on two technologies. In particular, one of the promising ones is really mineral carbonation, okay, or sometimes you'll hear this called carbon cured concrete. Some of you might be familiar with it. That's kind of what I'm going to look at today here, except we're going to look at it from a soil stabilization perspective. Why would we care about this? Well, basically the subgrade quality has a substantial impact on the overall design and cost of building a pavement system. So generally speaking, you'll have up here your asphalt. This is what everyone sees. That's what's cracking. That has to be the problem, right? Well, there's a lot more going on. We also have this base, subbase, and often native subgrade material that's contributing to the distress that we see in the pavement. Certainly here in Maine, we see the potholes in the summer, we get the freeze, and then the thaw cycles here when March, April come around, lots of rain, and then we see things start to a lot of distress start to take place. And basically, when you have a better subgrade, all right, and I'm using CBR, the California bearing ratio, which is really a proxy for stiffness here. For that, all right, as that increases, these other materials decrease, and so that substantially reduces the cost, and you can also increase the durability of the pavement system. And so here's another way to quantify it here, subgrade CBR, and we see that if we attribute it across this family of curves here, these brown curves, the cost is going to go down as that CBR goes up. All right, this is a relatively old figure here that's making some estimates as to how that would contribute to cost, but generally you get the idea. So there are many ways that we can potentially improve the subgrade or materials that are underlying the pavement, especially when we have problematic materials, which is not always the case. But when it is, we can excavate and replace. Okay, we can use geosynthetics. These two tend to be pretty expensive. This works pretty well. This is sometimes has some questions. It's not widely used. And then here at the end, we have chemical stabilization. And really what we're trying to do here is to prevent, I've shown you some photos here of really what's going on underneath the asphalt. This is a dirt road, but this is something that could be underlying the asphalt, all right, on an engineered in an engineered system, all right? And so we don't want to lose that bearing capacity, right? We want to make sure that that remains stiff. Okay, so how are we going to do this? We're in this class of what we're calling chemical stabilization, and we're going to do things a little bit differently. Now with chemical stabilization, if I go back here, you'll see you basically have a big rototiller here mixing cement or lime typically into the soil. Okay, and what that's going to do, you're going to have a hydration process, and it's going to stiffen up the material. If we think about the process of where that cement comes from, right? Really, we're thinking about stabilizing weak soils now and putting carbon back in the ground, where it belongs, where it started. Okay, where did it start? It started in a quarry as limestone. That's often calcium carbonate. Okay, we come down here, we typically heat it up. All right, and this is usually where the process stops. So we heat it up, we get lime cement production, and we off gas all that CO2 as the calcium carbonate decomposes. Okay, and so that's what we call process-based emissions. All right, and those process-based emissions account for approximately 2/3 of those CO2 emissions that you see from lime or cement production. All right, so it's a substantial amount. So what we want to do is take that CO2, actually mix and add it back into the ground with the lime, and basically come back to calcium carbonate. So we just want to kind of make that entire cycle, and we're going to rely on calcium carbonate to be our binder, all right, instead of hydration products that you would typically get with cement. If you think about the reaction rate here, the whole point is we need to get carbon dioxide into the ground then. I'm going to show you a photo here. Really, these are thermal images. Top down, we're introducing carbon dioxide, and it's penetrating down here. And because the reaction is exothermic, it's generating heat. So we can see where the reaction is occurring here in this particular experiment. So you've got lime, water mixed with soil. We're introducing the carbon dioxide. And what's happening here, where you see things lighting up, calcium carbonate is precipitating, and we're generating heat. All right, so that's kind of a proxy for where the reaction is occurring. All right, if you kind of pay attention there. This particular experiment, by the way, you can get things going pretty rapidly, but overall it took us 15 minutes to go the depth that's typically improved with chemical stabilization, anywhere from 6 to 12 inches, typically speaking. One thing that people are going to ask is, all right, does it perform as well as the hydration products? And so with the materials that we've tested, granular materials, fine grain materials, the answer is yes. So I'm not going to go into the details of this figure, but I'm showing unconfined compressive strength and basically this ratio of density, all right, and then also the volumetric binder content to play into the strength that you get. So those are important design parameters. But generally speaking, what I want to show here is that they follow the same trends, all right, and effectively overlap what you'd expect with cement, okay, using chemical stabilization. So what we did after the lab is we wanted to go in and start thinking about a prototype, all right, something that could potentially be applied over large areas. And so we call this kind of accelerated surface carbonation, where you would expect, let's just say, a seal, all right, introducing carbon dioxide beneath it, trying to enforce vertical penetration and getting that carbonation to occur where we have some lime mixed soil now. Here's kind of an idea of what that looks like. That red is trying to poorly illustrate here a portion of the embankment that we're simulating. And so that's kind of what you're seeing here. This was heavily instrumented, all right? It's kind of intended to be a portion of the embankment, if you will, a roadway embankment. We see we have a gas reservoir, we're introducing it. We have embedded thermocouples and other instrumentation to look at what's going on. We also took it into an environmental chamber, introduced multiple freeze-thaw cycles on a silt, which is a highly frost-susceptible material. So we kind of interested in how durable it might be as well. Through the experiments, what you'd see here during the carbonation period, if you will, you see heat. This is basically at the surface. This is 100 millimeters down, 6 inches down, 4 inches down, excuse me. You see this heat start to generate, similar to what I was showing before. So we knew the reaction was ongoing. But more importantly here, you see the shear wave velocity, basically a geophysical method to give us an idea of how stiff the soil actually is. We drop from here to something that's typical of a soil, like you'd expect, and it jumps up here to something that you'd expect to be representative of really soft rock. If you're interested, I brought an example that you can feel if we want a little show and tell, and you can feel that is in fact the case. All right. If there's some pavement folks in the room, yes, we did carbonate, certainly in the upper portion, all the lime that was there. So we converted all that lime to calcium carbonate. So now we have the carbon basically embodied in the binder, and we get this substantial increase here at the surface of the CBR. And this would be considered basically a very good or excellent subbase. Okay. Went through the freeze-thaw cycles. Basically, the shear wave velocity remained high, and through the carbonated zone, we see that the CBR also remained high. That was the red dot beforehand when it was just saturated, when we saturated the box. So overall, though, there are other things going on in industry. We have carbon-cured concrete. We have something that I'm presenting here today, accelerated carbonation to stabilize soil. And there are reasons to consider using these things today. A lot of folks would potentially see something like this and think, oh, that's great. We should just go ahead and use it. There is an added step. We have to add CO2. That is going to add some cost. We haven't found a silver bullet yet. And so what you're seeing now is incentives start to come along. So when we think about who might buy, well, we have public agencies. And in large part, this could be FHWA, state DOTs, potentially municipalities. All right. But there's some cost there. And then contractors. What are contractors actually going to use this? They're going to use it, all right, if they're told to use it. Right now, there's not necessarily a big incentive to do so. But what I see as the potential motivators here, when we're talking about public agencies, really now there are financial incentives with the IRA, the Inflation Reduction Act, $2 billion out there to offset costs of using new processes and materials that substantially reduce the carbon footprint, okay? You'll also see state legislatures now in some states actually moving towards a really encouraging policy that would encourage folks to use these types of materials as well. So these are the types of things you start to see happening in the country. So from the contractor perspective, there are also bidding requirements that are starting to be developed when you talk to folks that are not just going to talk about how many dollars, all right, are in the bid. They're also going to ask how much carbon, all right, you're actually reducing through your construction practices, all right? So those things are starting to creep in now, and they're motivated in part by this, all right? So the other reason that a contractor might want to start getting involved with things like this is risk of fear that they'll get left behind. Because ultimately what this might produce, all right, or might incentivize or get things going is states might start moving towards mandates. All right. And so I always use the analogy, we can't dump chemicals in the Penobscot River anymore from the mills. All right. So that opens up a new market, and we have to figure out how to clean those things up. All right. And so that might be a similar thing here. All right. So that's kind of how I see this working. Definitely the public agencies, contractors, and people building this, are intertwined. So will that ultimately be enough? Folks that are betting on these technologies working and developing them and trying to commercialize them are really betting on they'll meet that moment where folks are going to be trying to use these in large quantities. And that's kind of my take on it. So thanks, everyone. Appreciate you taking the time to listen.